you guys to be so kind, after you've decided on your groups, I want you to come up here and congregate here-ish so that you can see what I'm doing. It's going to be hard to see from the back, because this is what you are going to do in your groups. All right, and I need a volunteer. Yay. All right, if you could hold that, and then we're going to put it on the floor. I have these pull-out cars that if you look at page 19, you're going to be pulling back the cars a certain number of inches. It's specified at the top. You're going to do 3 trials for each distance. Let's set it down on the ground. It's really helpful if you start the tape measure right in the corner of one of these squares on the floor, one of the tiles. The tiles are exactly 12 inches long. You want to see how far your car is going to go. So you need somebody that's in charge of the tape measure. That's going to be one person in the group, laying it out. They're going to have to hold it still. So the first one is like 2 inches. And then you've got 4 inches, 6 inches, and 8 inches. So for, say, the 8-inch one, here's my starting line back here at 0. I'm going to put the car at the 8. I'm going to pull it back until it's behind the starting line. Behind the starting line, and then you're going to release it, and you're going to see how far it goes. It ran into my tape measure, but you're going to see how far it goes in this horizontal distance. Sometimes they're going to veer off to the side. You're still just measuring how far out it makes it, okay? You guys have 10 minutes to collect your data. You need to come up and pick out a pullback car. You need to grab a tape measure. So somebody's going to be pulling the car back, somebody's going to be holding the tape measure. Third person is going to help decide how far out it went and then recording those values, all right? Like I said, you guys have 10 minutes to collect your data, and then we'll figure out what we're doing from there. 10 minutes starts now. So after we're done with the lesson, we're going to go through the notes. I'm going to show you how to do an analysis of this, and you're going to decide on the best model. You are going to be racing your cars. We're going to do this in the hallway because we're going to do groups of 4, and then we'll race the 2 winners from that. I think it's going to end up being a group of 4 and a group of 3. But the top 2 winners then will have a face-off. I will tell you how far your car needs to go, and the goal is to get it to go as close as possible to the finish line without going over the number that I give you, which I have not given you yet. We're going to get as close as we can to the finish line without going over. I wondered whose that was. All right, so I'm going to be using my data up here. You're going to be doing this with your data in your groups, but for right now, I just want you guys to kind of follow along. Hopefully somebody in your group has an iPad or a Chromebook with them. If not, you can do it on your phone, but the screen is so small it's kind of hard to see. Okay, so we're going to go to StatsMedic. And this is on today's page. If you look at today's page, come on, page down. Nope. There we go. There's a link right here to what we're going to be going to. This is where we're going to enter the data. Today is the 6th. All right, so our explanatory variable, this is the pullback distance. And this is going to be the same data for everybody. How many times did you pull it back for each measurement? 3, so you have to enter it all 3 times. So 2, 2, 2, 4, 4, 4, 6, 6, 6, 8, 8, 8. That should be the same for everybody. And then what is our response variable? Distance. The other one was distance also. Distance traveled. And this data is going to be different for everybody. I'm going to put my data in here. In your groups, you should be putting your data in. All right. After you get all of your data in, we're going to sketch a scatter plot. We're going to find the equation for the line of best fit, and we're going to sketch the residual plot. This first one, model 1, x versus y, this is our linear model. So this is just going to be a scatter plot of my data and the line of best fit for my data. We're going to click on Begin Analysis, and it gives you a scatter plot there. You want to sketch whatever your scatter plot looks like into your notes on the first XY axis there. Sketch your data there. For this part right now, before you guys actually start sketching, I want to run through what we're doing, and then I'll set you guys loose to do that on your own, okay? So you're going to sketch the scatter plot. We're going to come down here where it says Calculate Least Squares Regression Line, and I'm going to click on that. It gives me the residual plot, and it gives me the regression model right here. There's my equation for my line of best fit. You also want R and R squared. It gives you R squared, and then you would take the square root of that to get R. Or if you want to cheat, you can click on Calculate Correlation, and it'll give you R right there. So that's the first thing you're going to do. When you hit Begin Analysis, it'll show you the scatter plot. Then you have to click the button for Calculate Least Squares Regression Line. That's where you get the equation and R squared from. And then you can either square root it or hit the other button to get R. After you do that for your first model, model number 2, you're going to do a quadratic model. So model number 1 is linear. X versus Y. Model number 2, we're going to do X squared versus Y. So this is a quadratic model. You're going to have to change your input. You are going to do an exponential model. For your exponential model, you will go back to your original x's, 222, 444, 666, 888. And now you're going to need to grab a calculator, and you want the log of your y values. So you're going to enter the response variable data differently. You're going to do the log of the y values and input all, 12 of those. And then you're going to run the regression, sketch the scatter plot, find the equation, find R squared and R, sketch the residual plot. All right? I'm going to give you guys, let's see where we're at in 10 minutes. If we need more time, I can push it out a little bit more. But let's see how far we can get. 3 models. Try to get through them in 10 minutes, and I will be coming around the room to help if you get stuck at any point in time. All right, I know I still have several groups working on like either Model 3 or they're still on Model 2 finishing up. I'll give you guys some more time here in just a minute. But some of my groups are finishing up, so I want to kind of push forward with this, and then you guys will get some more time, and I will let you know the distance that you need to try to predict the pullback distance for. All right, so when we're choosing the best regression model, there's 3 things that you want to look for. So this is what you're going to be looking for on your models. Check the scatter plot for a linear pattern. If you don't have a linear pattern to your scatter plot, like, ooh, go away. At my scatter plot right here, see how mine has this really obvious curved pattern to it? I'm not saying yours does, but mine has a curved pattern to it. That's not going to be a great model. A linear pattern in your scatter plot. You want to check the residual plot for no leftover pattern. And then you want to check for the R squared that is closest to 1. Whatever best meets those 3 criteria, that is going to be your best model. So I want to practice that right now, and then I'm going to set you guys loose to finish up your stuff, and I'll let you know the distance that you need to predict for. So I want to look down at the check your understanding here. Gapminder is an organization dedicated to studying global health. Here's a scatter plot showing the average annual income in thousands of US dollars and the life expectancy in years for a random sample of 15 countries selected from Gapminder. The output shows 3 possible models for predicting life expectancy from income. Model A over here is based on the original data, so this is a linear model. Model B and Model C involve transformations of the original data. You can see down here in the equations for the line of best fit. I want to use each model to predict the life expectancy of residents of a country for which the average annual income is $80,000. So grab a calculator. Grab a calculator. How do we calculate the life expectancy for Model A here? What are we going to do? For Model A. We're going to insert the income into the equation. How are you going to enter the income? What number are you going to use? 80. They're measuring in thousands, so you want to just enter 80. Don't enter 80,000. So go ahead and do that on your calculators. 69.9352 plus 0.1530 times 80. And we end up getting what? $82.175. All right, now for Model B. What did they do to transform this data? They took the natural log of the x's or the y's. Of the y's. How do you know it's the y's? Natural log is next to life expectancy hat. Life expectancy is the output. It's on the y-axis. So I want you to use this model now to predict the life expectancy for a country in which the average annual income is 80,000. It's okay. When you just plug in the 80, you get a pretty small number, right? Do you think that means the average life expectancy is 4-something odd years? No, that's the natural log of the life expectancy. What do I need to do so that it's not the natural log of the life expectancy, but it's just the life expectancy? Not square it, because that won't undo a log. What'd you say? E to the power of the answer that we got. Why is it E? Why not 10 like yesterday? Because it's a natural log. So we're going to do E to the power of 4.4116. We're coming up with what? I got, 82.4, right about. And now I want you to do Model C. Yep. right here. Yep, they said 80,000 and they're measuring the dollars already in thousands. That's where the 80 came from. What are we getting for Model C? We have to do e to the power of again, right? But we have a natural log in our equation also. So when you go to enter this into your calculator, 4.1393 plus 0.0603 times the natural log of 80. Because they did natural log of the x's and the y's. We end up with about 4.4035. So then we have to do e to that power. Does anybody have a best guess? Yep, 81.7 something. Which of these three models, because they all had different answers, which of these three models would do a better job predicting? Model A, Model B, or Model C? What are some things that we want to check for? Linearity in our scatter plot. Highest R squared, closest to 1. What else? There was one more piece. The residual plot. What do we want to look for in the residual plot? Yeah, the one with the least amount of pattern. Which of these three has the most linear looking data and the scatter plot that looks like the most random scatter, like the least amount of pattern? Probably C. Like, I notice on Model A and Model B, there's this one weird point. When I look at Model C, it actually is much closer to that line of best fit. And the data is closer to the line of best fit here too. In my residual plot, that is the least pattern-like of all of them. So Model C would do the best here. Scatter plot is most linear. Residual plot has no leftover pattern. Like, I don't even see the wave pattern that the other two kind of have going on. All right. I'm going to give you guys 5 more minutes so that we have enough time before the bell rings that we can do our competition in the hallway. You want your pullback car to get as close as possible to, without going over, 120 inches. 120 inches is your target number here. So you have to decide whether Model A, B, or C, Model 1, 2, or 3 on the front side is your best model, and use that to predict how far you would have to pull back your car so you can get it to go as close as possible to 120 inches without going over. Prizes for the winning group.